Hey everybody, this is the video lecture for the fifth section of the Counting Methods and Probability Theory chapter. The section is called Probability with the Fundamental Counting Principle, Permutations and Combinations. Before we get started, I want to point out two things. One, there's not a new outline or set of notes for this section because there's no new math in this section. And secondly, you'll notice that there are no recommended problems from this section. If I put any of these problems on the exam, it will be because it's an extra credit question. What we're going to do in this section is talk about how to combine all of the counting techniques from the first three sections with those fundamentals of probability that we saw in the last section. And because these problems tend to be a little bit more complicated, I have on the first slide here a suggested process for finding these probabilities. First, find the denominator, which is the total number of outcomes in the experiment. This is usually the easier of the two pieces of the probability to find. I guess that's opinion, and you might disagree in certain problems. But because there are fewer restrictions on the denominator, on the total number of outcomes, that's usually the easier one to do. Then find the numerator using any restrictions on what your event is. And then you have to write your final answer as a fraction. That's what you'll notice I do most of the time. Or you can turn it into a decimal or a percent if you choose. The first example will come from page 317, and it has multiple parts. I just picked a couple of them to demonstrate. So problem number 4 says 7 performers, which he named A, B, C, D, E, F, and G, are to appear at a fundraiser. The order of the performance is determined by random selection. So they're going to randomly decide who goes first, second, third, fourth, fifth, sixth, and seventh. Part B of that problem asks us to find the probability that E will perform sixth and B will perform last. So to give us a little more space, I've put the important information on the next slide. The probability that E will be sixth and B will be last is going to be the total number of ways that E can be sixth and B can be last over the total number of ways that we can order all of the performances with no restrictions. And that denominator is probably the easier one to do. Let me give myself 7 blanks, one for each performer. And let's pretend like they've put the 7 names into a hat and they're just going to draw one out at a time. So the first time they reach in to pick the first performer, there are 7 potential options in the hat. But then they're going to take that option out once it's been selected. So there are 6, and then 5, and then 4, and then 3, and then 2, and then 1. And 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. Another way to think of this is that it's just 7 factorial, and then you can put 7 factorial into your calculator and get 5,040. The numerator has a restriction on it because we're saying that person E has to go sixth and person B has to go last. I still have 7 performers, so there are 7 blanks, but now we only have one choice for the 6th blank because this must be person E. There's a restriction. And we only have one choice for the last blank because that must be person B. They have to go in the last blank. That leaves 5 performers to put into the first 5 slots. And we could pick any of those 5, right? Pretend like we took E and B out of the hat and we said, okay, they're our headliners, so we're going to have them go last. And now there are 5 performers left. We're going to put them in randomly. So there's 5, and then 4, and then 3, and then 2, and then 1. And if you multiply all of these together, you'll get 120. Or you can do 5 factorial, right? Because these two we don't need to order. We just need to order the 5 who aren't going into specific spots. The last step is to just turn this into a fraction. The probability that E goes sixth and B goes last would be the number of ways that E can go sixth and B can go last, divided by the total number of ways that we can order all 7 performers. And then you can reduce that fraction. And I can see that this reduces to 1 over 42 using a trick. If you look at the numbers in the numerator, they're 5 times 4 times 3 times 2 times 1. I'm not going to write the times 1. And in the denominator, it's 7 times 6 times 5 times 4 times 3 times 2 times 1. And I can cancel the 5s and the 4s and the 3s and the 2s, and it leaves a 1 in the numerator, because everything canceled out of the numerator, and it leaves 7 times 6, which is 42 in the denominator. But I want to show you how you can use your calculator to reduce fractions in case you're not familiar. So I can put 120 divided by the fraction bar is just a division symbol, 5,040. Then you push your math key, the same one that we use to get to all of our probability options. And the very first option says change my answer into a fraction, which seems silly right now because our answer is already a fraction, but it will reduce that fraction to lowest terms. So you can push the enter key or you can push the 1 key. And when you hit enter, it'll give you the reduced version. You don't need to reduce for me, but it dawned on me between making the last video and this video that if you're checking your answers in the back of the book, those are most likely going to be reduced. So if you have answers with ridiculously big numerators and denominators and you don't know how to reduce it by hand because the factors are hard to find, you can use the calculator to reduce. But I would be happy with the answer 120 over 5,040, or you could get some decimal approximation with your calculator. That doesn't matter to me. So notice how we approach the problem. First, we found the total number of ways that all of the objects could be used, the total number of options in the experiment. Then we found the numerator, which uses the restrictions on the event, and then we just made a fraction out of it to get the probability. So if they truly selected at random, there's a 1 in 42 chance. That's a little less than 2.5%. A little less than a 2.5% chance that E could go sixth and B could go last. Same scenario, but a different probability. Find the probability that F or G goes first. The denominator in this one's going to be exactly the same. We're still arranging those 7 people in any possible order, and so that's still 7 factorial, which is 5,040. The numerator, though, has a different restriction on it. Instead of saying that we have 2 specific performers that have to finish, we're saying one of these 2 performers has to go first. So the restriction we have to deal with is in the first spot. So there are 2 different performers, F or G, that could go first. We didn't put 2 people in that slot. We just have 2 choices. We've only selected one of those 2 people, either F or G. So when we select one of those 2 performers, that leaves 6 people for the second spot, and then 5, and then 4, and then 3, and then 2, and then 1. And you want to multiply all of these together, and that's 1,440. So the probability that either F or G goes first is 1,440 divided by 5,040. And if you reduce that fraction, it will reduce to 2/7. And did I do that because I'm some sort of math wizard? No, I cheated. Look at the numbers in the numerator and denominator. Almost all of them cancel. What's left behind? 2 divided by 7. 2/7. I didn't do that in my head. I just looked back at our work. If you think about it, 2/7 is a reasonable answer because there were 7 total people, and if one of these 2 people has to go first, the probability that one of those 2 gets selected is 2 out of 7. Number 7. This one you guys might like if you're into the lotto. A player wins the Mega Millions jackpot by matching all 5 white balls, which are numbered 1 through 56, and then the gold mega ball that they select at the end, which is 1 through 46. What is the probability of winning the jackpot? Okay, this one mixes fundamental counting with combinations. Those first 5 balls can come out in any order. It doesn't say we have to match those in order, so you can match any of those 5. So there are 56 white balls, and we're going to choose 5 of them. That's a combination. But then we also have to get a mega ball. And there are 46 mega balls, and they're going to select one of them. So I guess that's 46C1, but that's also just 46. Now I was able to do the arithmetic on the last 2 slides because I had some of those numbers memorized. But these I can't do in my head. I'm going to have to run to the calculator. Going to the calculator. There are 56 white balls, and we're going to choose 5 of them. So math, scroll to probability. We want choice 3 because the order doesn't matter. 5. So that comes out to, what is it, 3,819,816. And then we're going to multiply that by the number of megaballs, which is 46. So what number is this? This is 175,711,536. 175,000,000, already forgotten, 711,536. The numerator doesn't take any fancy counting techniques. How many different ways can you win the jackpot? You have to have the one ticket that has the right 5 white balls and the right Mega Millions ball. There's only one way to win, and that's to match all of those. So you don't really have to count that out. So the probability that you win the jackpot is about 1 in 175 million. It's actually slightly worse than that. And you might say, well, why does anybody play if the odds in winning are like 1 in 200 million? Well, it's the huge prize that they offer. The book mentions that sometimes the prize gets up to $656 million. And so, yeah, you only have a 1 in 200 million chance of winning, but the prospect of winning that much money makes people want to play anyway. Number 11. A box contains 25 transistors, 6 of which are defective. 6 transistors are selected at random. So you've got this box and they're just going to grab 6 of them. Find the probability that all 6 are defective. For the denominator, we've got 25 transistors and we're going to choose 6 of them. And the order in which we select them doesn't matter. Because we're just grabbing a collection of them, the order in which we grab them doesn't matter. So this is 25, choose 6. I cannot do that mentally, so I'm going to go to the calculator. 25, math, scroll to probability, choice 3, 6. That's 177,100. There's almost 200,000 different ways that you could grab 6 of those 25 transistors. The numerator says find the probability that all 6 are defective. This is just like the lottery problem. If there are 6 defective ones and you need to choose all 6, there's only one way to do that. But I want to show you that combinations will give you the same answer. There are 6 transistors that we've selected and we want all 6 to be defective. So what is 6 choose 6? That's the number of ways you can choose 6 objects from 6 objects. So it better come out to 1. 6, math, scroll to probability, choice 3, 6. So that's equal to 1. I'm pretty sure the calculator gets offended when we do stuff like that. That's like when people type 1 plus 1 in their calculator or something like that. But we had to check. So what's the probability that all 6 are defective? Well, it's 1 out of 177,100. And this is an example of how probability is used in real life. This is like a quality assurance issue, right? So somebody's working for the company that gives out these transistors, and they grab a box of them, and they know that some of them are going to be defective. But if they grabbed 6 that are defective out of 25, even if there were 6 defective ones in the box, the probability that the 6 that you grabbed would all be defective is really, really low. It's so unlikely that there were only 6 and you grabbed all 6 defective ones that the assumption would be that there are probably more than 6 defective ones. So maybe the quality of this thing needs to be improved. Same setup, but now we're going to find the probability that none of them are defective. So what's the denominator? Well, it's the same, 25 choose 6, which I think we said was 177,100, 177,100. And what's the numerator? Now instead of selecting from the 6 broken transistors, we're selecting from the transistors that work. So how many of them work? Well, the other 19. So of the 19 transistors that work, we're going to choose 6. And what is 19 choose 6? I don't know. It's 27,132. So the probability that you select all working transistors is 27,132 divided by 177,100. I don't have any fancy reducing tricks for this one. So I'm going to run to the calculator and ask the calculator to reduce this. So 27,132 divided by 177,100. I'm going to push math, very first choice, and then the enter key. And it says it reduces to 969 over 6,325. And I still don't really know what that number means. Like, you can kind of estimate it. It's pretty close to 1,000 out of 6,000, but most of us wouldn't be able to figure out what that is. So I'm going to take that same original. I could take the reduced version, but I want to show you. And just get the decimal. It's around 15%. 0.15. I guess this is an approximation now. There's about a 15% chance. Why did I turn that one into a decimal? Because the fraction wasn't very enlightening. Right? I know what 1 out of 177,100 is. I know, for instance, what 1 out of 42 is. I have a good feel for that. But that fraction that we got, that 900 number, what were those numbers? 969 and 6,325? My number sense doesn't really tell me what that is. I mean, I can approximate it, I guess. But I'm much more comfortable looking at it as a decimal than I am a fraction. One more. Problem number 14. Next page. A parent-teacher committee consisting of 4 people is to be selected from 15 parents and 5 teachers. Find the probability of selecting 2 parents and 2 teachers. Okay. So if they're selecting 4 people from this entire committee, and there are 20 people, because there are 15 parents and 5 teachers, then the total number of options we have is 20 choose 4. 20 choose 4 is 4,845. And in the numerator, we have to select 2 parents and 2 teachers. So it's like there are 2 blanks. Of the 15 parents, we need to select 2. So that's 15 choose 2, which is 105. And of the 5 teachers, we need to choose 2. 5 choose 2 is 10. And so that's 1,050. So we get 1,050 divided by 4,845, and that looks like it's going to reduce quite a bit. So I'll check it with the calculator. 1,050 divided by 4,845. Let me see what the fraction is first. 70 out of 323, that's a decent answer. Maybe you don't like that answer because you don't have a feel for what that probability is. So just use the decimal instead. I'll show you this time that you can use the reduced version. So it comes out to around 21.7% approximately if we round. A little more than a fifth. The probability that the committee has exactly 2 teachers and exactly 2 parents would be about 20%. That's the end of this lecture. I do want to point out that we're skipping the next 2 sections because we lost that week when we extended spring break. I had to cut a couple of sections out, so I'm cutting out the next 2 sections. We're jumping to the end. We'll do 2 days on that, and then we'll have a day of review, and then the next exam will come after that, and I'll be giving instructions for that when it gets closer. Email me if you have any questions.